And I'll say welcome back everybody to PCB Design Fundamentals Part 2. I'll ask one last time for the last few people who have just signed in. Does anybody have any questions that you want to go over before we get started on slides for today? Right, no questions. Oh, I was also informed by Ivan that Ivan and Kelly that they should have gone in and verified that everybody should now have access to the DRM standards here in the course page. So if you go into our Edge page here, uh, where is it? Sorry, did I miss it? That's rigid flex. I may have scrolled past it. Q4 of 23 PCB design to Q4 of 23 here. So if you scroll down to the bottom of our Edge page, I was told that everyone down here now, if you go in as a student and view, and yes, it looks like everybody in the class now has been updated. So please let us know if for any reason you're still having any issues trying to access the DRM content. So for me, unless I go actually view it, I won't actually see your username and credentials here. Uh, and so this is not what you'll see. You'll see an actual, this is your email, this is your credential, password, and so on. So for the DRM credential issues, those have all been updated now. So if anybody out there was still having any issues, it does look like everybody has been populated now. All right, with that, let us go ahead here and get started on today's slides. Uh, So this is the big week, folks. This is the week where we are going to talk about signal integrity. Now, again, signal integrity in and of itself could be an entire college degree program. It is very extensive, getting into all the nuances. I'm going to touch on the big three items here, and we're going to talk about them at a level sufficient that you have the knowledge and understanding you need to ask the right questions and implement good practices, but there will be times where you'll need an actual signal integrity engineer or electrical engineer to maybe do some more focused design and analysis work here. So our topics, we're going to talk about signal integrity, overshoot and undershoot, termination, crosstalk, rise time, fall time, as well as transmission lines and power distribution networks here. Part of power distribution networks, we'll talk about our decoupling capacitors. Again, this is very um, subtle work, not subtle. There's going to be a lot of nuance here and a lot of paradigm shifting in how I discuss this. So if at any time you guys have got questions, just raise hands, ask questions. Okay. So first off, the question that gets asked, what is signal integrity? Signal integrity is the prevention of signal distortion, i.e., or as an example, if you have too much distortion on, say, a square wave, you'll look at it on an oscilloscope and see that the edges of the square wave start rounding off, and this is usually due to excess capacitance or other parasitics. We also want to prevent a reduction of signal to noise ratio, or SNR, i.e., when the voltage level of a signal is reduced to the point where it becomes indistinguishable from the noise, you have a zero signal to noise ratio. Your signal level is the exact same magnitude as your noise, or vice versa. We want to avoid this. We want our signal to be of sufficiently greater magnitude than our noise uh, to be distinguishable, to be able to be understood. Uh, SNR reduction, I should say. SNR reduction happens whenever the noise interferes with the proper operation or behavior of the signal of interest. So basically, when we get our signal to noise ratio reduced to the point where the noise interferes with the proper operation or behavior of our signal of interest. Now, I'm going to give you a couple of quotes here out of one of my most favorite go-to books, or one of my key go-to books for signal integrity discussions, from one of my own mentors here, Lee Ritchie, uh, and if you read my syllabus, if you read the syllabus for the class, it's listed as one of my reference books here. So from Lee Ritchie's books, Right the First Time, Volume 1, is out of TTL engineering has grown a collection of assumptions about electronics. And among these are, there is no time delay between inputs and outputs. The voltage waveform at both ends of a wire or connection are the same. Power distribution system is ideal. IC packages are ideal. Driver outputs are ideal. Signal inputs are ideal. Connectors are ideal. Wires have no delay. Wires are ideal. Noise is not a problem. Now, notice a recurring theme in many of these early statements here. This idea of ideal, ideal, ideal. Okay? So, and because of the way we teach electrical engineering in universities, and I'm guilty of this myself, having teaching, uh, university level courses myself, the way we teach electrical engineering is fundamental building blocks. And if we try to, from day one of teaching engineering courses, try to explain parasitics and uh, the fact that for every capacitor you get a free inductor and a free resistor and so on, we'd overwhelm our students. So the nature of the way we teach engineering as these distributed models, ideal components, R's, L's, and C's, and so on, leads to this misconception that everything in electronics can be treated as ideal components. Okay? The reality is there is nothing ideal in electronics or the world as a whole. All components have parasitics due to packaging. Example, all traces have an inductance in addition to the resistance of the trace that was historically ignored as not a concern. Again, in older legacy designs, the inductance of the trace was so small compared to the rest of the design that it was a non-issue. But as traces have gotten narrower and narrower, features have gotten smaller and smaller, etc., now these parasitics are becoming problematic and we'll have to deal with them. Now, from electrical engineering, we can say that the voltage across an inductor formed by a trace can be approximate, or any inductor actually. Our first order voltage equation for the voltage on an inductor is L times di dt. Hopefully this does not bring back too many flashbacks of calculus classes with derivatives and so on here. But if we recall back to our calculus classes, that the derivative really means change, right? It's change in time or change in current over a certain amount of change in time. So di dt could also be written as delta I over delta t, change in current over change in time, or change in current per unit time. Okay. Now, and this is where we say voltage is V. V is voltage in volts. L is inductance in henries. Di is change in current in amps. Dt is change in time in seconds. And now for the dt term, change in time, for a square wave, we already know what that change in time is. We call that the rise time. We could also use the fall time, but we primarily use the rise time. So we can modify this equation to be di, change in current, over rise time. That's our change in time. Okay, so from this we can get a very simple first order approximation. Again, for those that studied your electrical engineering, we know that this equation gets very complex very quickly, especially when dealing with alternating currents, alternating time varying currents, time varying voltages, and so on. But it's a good first order approximation. Okay. All PCB transmission lines are non-ideal due to material and manufacturing tolerances and the parasitic parameters, and all non-ideal characteristics lead to degradation of the signal being sent by the driver to the receiver. Signal integrity is a measure of how close to ideal the real signal is, and signal integrity methods are a series of design tools used to mitigate the degradation of the signal of interest and to maintain the signal at levels within an acceptable margin along uh, the entire transmission line. Then the next big question that gets asked all the time, at what point do we need to consider adding SI uh, design considerations to the project? And I already have it stated up here. SI is for signal integrity, not SI for metric. Système internationale, the French term for the metric system that we use. Um, Instead, SI in this case, I'm referring to signal integrity. So at what point do we need to consider adding signal integrity design considerations to the project? Well, and I'm going to come to this first bullet last, but, well, you may have failed FCC testing. Now, um, or I'm going to put it like that, or appropriate local regulatory compliance. FCC is the U.S. based for radio signals, EMI, RFI, interference, and so on. So wherever you are in the world, um, if you're over in Europe, the Europeans have their own. I believe it's IEC sets the EMC compliance, regulatory compliance, which I believe piggybacked on what the FCC did way back in the day, but I could be wrong. But anyways, wherever you are, and Mexico, I believe you guys have just borrowed FCC compliance and so on. I think Canada, I think with that whole NAFTA thing, I think all three, Canada, US, and Mexico, all agreed to have the same regulatory compliance for EMC. But anyways, point being is you fail your EMC compliance. You may have intermittent failures. You may be sensitive to power supply variation. You may be sensitive to temperature variation. A product works in the lab but not in the field. Boards must be matched to work correctly. This actually, one of my very, very first jobs back circa 1992, 93 time frame, early 1990s. I was working at this company in Michigan, and they literally had this process. They thought it was just fine, where when they'd get a batch of new boards in for the product, they'd literally go through and have a batch of the processor boards and a batch of the sensor boards. And they would have a technician take a processor board, plug a sensor board in. Does the system work? No. Get a different sensor board. And you'd keep matching them until you had a matched pair that said these two boards work together. This is one system. And that says your design is so marginal, right? The time that's working. And then the final one, the most insidious one, is bullet one here. Something used to work and now it doesn't after. And insert your after condition here, right? After condition, changing part suppliers, changing fabricators, and the dreaded nothing. You did nothing. You reordered the exact same design, and the new design comes in, and now it doesn't work. The changing ICs or IC suppliers is particularly difficult, especially for products that used to work and now don't. This is actually something I'm teaching my students at university right now. I've taken on teaching a class, an introductory class in silicon design. When an IC supplier improves their process, this often leads to smaller die. Die is the term for the piece of silicon inside the IC chip that actually has the circuitry on it. So we call those dies and so on. So when the most common practice that we see is the silicon designers, and you've heard this in the news, especially with the high-speed guys, the Qualcomms and Intels and AMDs. We're working in the 45 nanometer node, the 22, the 16, the 9, the and so on. And there's commercial products out there in 5 nanometer now. I know some companies are starting to work in 3 nanometer, and I know at least one company that is experimenting in 2 nanometer process. More on what that means here in a moment. But as you continually shrink the silicon, they say it's new and improved. It's as good or better than what we spec. And while that's great for the IC suppliers, it wreaks havoc for us, and we'll see why here shortly. So it leads to smaller dies. Smaller dies in turn leads to smaller channels, which in turn leads to faster rise and fall times. Faster rise and fall times means higher frequency content in the waveform, and higher frequency content means higher sensitivity to signal integrity issues. There are four main areas of signal integrity: power distribution network, or PDN quality; EMI, radiation emissivity or susceptibility; crosstalk; and reflections. All four of these are related to the rise and fall time and the associated frequency harmonics. Now, I will make one other statement I should have made at the beginning of the slide deck. This set of signal integrity slides is primarily focused on our digital signals. Again, analog and RF signal integrity is a completely different beast. That's outside the scope of what we're going to do here. And so we won't be touching on those. We're going to be talking primarily digital. That's where the vast majority of all signal integrity work is happening in modern designs. The three key aspects of signal integrity with regard to current flow. Classic current flow, again, what we teach in university, is the movement of what are called holes. What actually moves from atom to atom in a conductor is electrons, but electrons flow in the opposite direction of classic current flow. Current always flows in a loop from the source of the current to the load and returning back to the source of current. Within any given loop, the current is going to be constant. It follows then that every signal has a return, and it is critical to understand where the return is and how it may interact with other signals. Key to the control of signal integrity issues is going to be the use of our plane layers. Planes provide many key performance improvements for signal integrity. They are necessary for proper controlled impedance. They are used to control EMI. They are going to act as a shield. They will also act, there's multiple ways they'll act as a shield, both in absorbing energy and restricting the area that the energy can move out to. We'll see that here shortly. They'll control crosstalk by reducing the field area and therefore reducing the cross coupling. And planar capacitance is necessary for high-speed switching and controlling VCC and ground bounce on the PDN. And they will minimize inductance of the PDN connections. And reducing the height between the trace and a plane further reduces EMI and crosstalk by concentrating E field and H field lines, similar to what I talk about here in bullet 3. As a refresher, electromagnetic waves. Again, if you go into RF engineering, I've had a few RF engineers tell me recently in my RF board class that there are special conditions or circumstances in which an electromagnetic wave can actually violate the classic rule we've learned. But for the purposes of this class, we are going to go with the classic statement here that says the EM waves are a electric field and a magnetic field. They are going to be the only wave that exists naturally in the universe. All other waves that we're going to talk about here, square waves, triangle waves, etc., even standard sinusoids that are not an EM wave representation, these are all man-made, and the only thing that actually exists in nature is an electromagnetic wave. This is the only thing that can move through free space. It is actually an energy wave made up of an electric field and a magnetic field. The two fields are always perpendicular to each other. So as the wave is moving through time, say the blue might be a representation of the electric field, and it is moving north to south as it's moving forward through time. And the green represents the magnetic field, and it's moving east to west, again, as we move through time here. Amplitudes are not required to be the same magnitude as depicted in the graphic right here. I might have a higher magnitude E field and a lower magnitude H field, or vice versa, or they may be the same magnitude. A quick discussion on RF signals. So radio frequency signals exist as a single sinusoidal frequency. Therefore, we will typically use frequency domain analysis. We'll use wavelength instead of period for a measure of one cycle. And frequency is a measure of the number of cycles in a given time, typically 1 second. Wavelength is therefore the measure of the distance traveled during one cycle of the waveform, and waveform and frequency are inversely related to each other, i.e., as frequency increases, wavelength decreases, as shown in this little graphic right here. A very low frequency signal right here has a very long wavelength. The distance between the peaks is very long. A very high frequency signal has a very short wavelength here. Also, as we talked about with a uh, frequency domain analysis, we're going to use measure distance. We're going to, this thing here called wavelength, we're going to depict as the Greek letter lambda right here. If we were in time domain, that same measurement here would be given a time called the period. Okay? Now, frequency relates to wavelength as follows. Note that v is equal to c in free space, where c is speed of light here. So the equation for frequency is given as f is equal to v over lambda, where f is frequency as hertz, or seconds raised to the -1. Right? Velocity is meters per second, or meters seconds -1, and wavelength is given in meters. So we have a velocity is meters per second, and wavelength is in meters, so the frequency will be given in seconds, but it'll be seconds to the -1, and so it'll be seconds to the -1 will be given the term hertz. Okay? Velocity versus material dielectric constant. Now, that's the next equation here. For a material with a known relative permittivity, the velocity can be determined using the following simple equation right here, where c is speed of light, v is velocity, and which we get from up here. So if we know wavelength and we know frequency, we can determine velocity. We can also derive velocity directly from here. If we know speed of light and we know dielectric constant, a little algebraic manipulation here. In our case, square root of dielectric constant is equal to speed of light divided by velocity right here. Also, we know that digital signals, square waves, are formed from an infinite series called a Fourier expansion using only the odd harmonics. Technically, it's all the harmonics, but the even harmonics technically subtract, and the odd harmonics are the ones that are going to add. And here we have f is frequency and t is time in this term right here. And from this, we can see that to properly produce a square wave of frequency x, we will actually need to handle 10x or even 15x for our design for legacy TTL. For modern designs, this is more like 50x to 100x. Okay, and so digital signals, as we said, are a square wave rather than a sine wave. A square wave is an infinite series of sinusoidal waves superimposed on each other. Now, in mathematics, we always talk about the zeroth frequency. That's the DC, or the flat line right here, so that can be ignored. The first harmonic right here, that's going to be our fundamental frequency. So let's say, for example, I want to make a 10 kilohertz square wave. First, I put a 10 kilohertz sine wave. Then I put a 30, then a 50, then a 70, then a 90, and so on. And I keep superimposing them. And where the sine waves are in phase with each other, they will add, and where they're out of phase, they'll subtract. And what we end up with is something that looks like this. And this is also one of the reasons why when you look at square waves on an oscilloscope, the two horizontal portions of the square wave always seem to have some fuzz or some noise on them, but the vertical sections don't. That's because you're seeing the results of this infinite series of this infinite Fourier expansion series right here. Okay? And I actually have a little simulation running using a very similar simulation equation to the one we just saw there. This is a slightly different form of using cosines instead of sines here. But if we take this, and as a digital engineer, I always start counting at 0. So my first harmonic here from 0 to 0, summation from 0 to 0, right here, and I've got something sinusoidal looking right here. Okay. If I count from 0 to 1, there's 2 harmonics. Notice there's still a pretty steep slope right here in my rise time. Okay. What if I go to 10 harmonics? again, you can still see a pretty appreciable slope right here in my rise time. Now, this is the point that I want to get across to you guys when it comes to these square waves. The frequency that you run your clock at, and we're going to talk about this here in a minute, your clock frequency has almost nothing whatsoever to do with your signal integrity. I have heard over and over and over again engineers tell me I don't have to worry about signal integrity because my fastest clock speed is only 100 kilohertz. It's ridiculously slow. And I said, yes, but what is the rise time? And the reason being is it's the rise time of the chips. As we shrink this silicon down, which we're going to see in the next slide, in order to achieve this fast edge rate, and let me just keep going here for a second, right? So I might have to have 20. I still have a bit of a slope edge right here. It's not vertical yet. So I might need to go to something like 50 or even up here to something like 100 to start to approach a vertical enough wall. Now that's the rise time. So if the silicon designers say this device creates a, say, 100 picosecond or 200 picosecond rise time because they've shrunk the silicon size down so much, that says you have to think about it in the reverse. If my rise time is that fast, my square wave is going to have this frequency content regardless of what clock speed. I'm going to have these higher and higher and higher harmonics that must be present in order to have this. Okay, and I know this is a little bit of a paradigm shift, so let me explain what I'm talking about here. Okay, so we know from semiconductor design that rise time and fall time are defined only as a function of MOSFET geometry and not the clock frequency. For this reason, we say that rise time and fall time and not frequency is the defining characteristic that's going to define when we need to use these high-speed design rules. Okay. So basically what I'm getting at here is that even if I'm running a slow clock, right, a very low clock frequency, in order to achieve these nearly vertical walls, I still have to have 150, 100 or more harmonics of that. So let's take a pretty standard clock frequency in most embedded system designs, 10 megahertz, right? We're still relatively low frequency comparative, right? Relatively speaking, somewhat low frequency. But if I have a 10 megahertz clock, but my devices are trying to generate, say, a 100 picosecond edge rate, that means I probably have, say, 200 harmonics of frequency content to get that sharp of an edge rate. If I'm at 200 harmonics of 10 megahertz, that means I actually have frequency content up into the 2 gigahertz range, which means my originally simple little digital square wave has now got actual real RF frequency content in there that has to be dealt with. So again, it's this edge rate, regardless of clock frequency, it is the edge rate, this rise time, fall time, the more that my chip is going to produce this, right? And this edge rate, even if I have a slow clock going into the chip, if the output driver pin of that chip says, well, I'm going to switch within 200 picoseconds, then I'm going to have that nearly vertical edge rate or rise time, which means I'm going to have this high frequency content in there regardless. So is that clear to everybody what I'm talking about here? Is that this edge rate is created by the driver pins of all of our devices. And as the silicon manufacturers keep making those devices smaller and smaller and smaller, they get faster and faster and faster. And therefore, the edge rates get faster and faster and faster, which means even running at slow clocks, the frequency content to create that sharp of an edge rate exists inside that square wave because of what we just talked about right here, the superposition, right? I only need 9 harmonics here, and I get a slow edge rate. Yes. Vibe, yes. Question?
Yeah, so you said that you're going to have higher and higher order sine waves or cosine waves into that square wave.
Mm-hmm.
So within the square wave, I know they get superimposed and makes it look like a square wave because they're like either additional or subtractional waves. What about like how does it affect SI? Is it because it's propagating as well?
Yes, they're all propagating. They're all superimposed on each other. So basically, and we're going to get to that here in just a second, but yes, effectively, that says that frequency content's there. So if you try to filter out the higher frequency content, oh, I'm going to put, a, uh, was it like, 50 megahertz filter on there. Well, now all of a sudden your square wave starts looking more like a sine wave, right? Because you've filtered out all the higher frequency content kind of things, right? That's one of the reasons why we have almost no RC filtering on digital signals. We just go from driver to receiver, driver to receiver. Because if I start filtering too much of that frequency content out, my square wave is no longer square. So all of that frequency content, anywhere that you see that uh, a square wave, if you measure that point with a spectrum analyzer, right, you will actually see power pulses all the way into these upper frequency bands and saying, yep, you actually have pulses all the way up to these higher and higher frequency bands, not just your fundamental frequency. So yes, you are correct that all that signal gets propagated along the line. It's part of the square wave. You can't have one without the other. Does that answer your question, Vibe?
Yes.
Okay, excellent.
Thank you.
Okay, excellent. No problem. Okay, so due to the square wave nature of digital signals, we are going to tend to analyze those in the time domain rather than the frequency domain. In the time domain, one cycle of a signal is measured as a time called the period, from rising edge to rising edge, and so on here. And then we have the amount of time that the square wave signal is at logic 1, or V high right here. We're going to measure that as another time called the pulse width. That's more just straight up for digital engineering. Don't need to worry about pulse width for this class here. Um, and so on. So we call the equivalent of the wavelength, we call it the period here in time domain. And additionally, for digital signals, we are concerned with the rate of change of the signal called the rise time, fall time. We've already mentioned that. Now, I like this graphic, except that the person who created it, and I borrowed this from Google, the person who created this has a incorrect title up here. This should say uh, pulse width, not period, because this is just the rise time to be period. This should have been measured all the way out to a second rising edge, but close enough here. The idea being is that when we have a signal that's at logic low and there is some amount of time, as much as I keep talking about it's getting faster and faster and faster, it's not zero yet. There is no such thing as a true step function. That's a mathematical construct. There is some amount of time in the real world for that signal to change from a 0 to a 1 or from a 1 to a 0. So that total amount of time it takes to change from a 0 to a 1, we call the rise time, and the total amount of time it takes to change from a 1 to a 0, we call the fall time. Again, those signals are getting faster and faster and faster, so it becomes problematic. So while the transmission line is being actively driven by the driver, the capacitance of the transmission line is being charged or discharged, the signal will not see any reflections. So this is something we're going to talk about here in just a moment. But effectively, during this time period right here, while I'm actively putting more energy in or actively taking energy out of the transmission line itself, I will have zero reflections because I'm actively driving. I'm overcoming any reflected voltage with new voltage energy I'm putting in, and so on. To determine the propagation delay of the trace, so we already talked about this on the previous slide, we use the following equation: root epsilon sub r equals C over V, where epsilon r is our dielectric constant, C is speed of light, V is velocity of propagation. So here's a fun little thought experiment I like to do with this. Okay. Whoop, I clicked on the wrong button. Sorry about that. Let me click back over here. Altium will open up in the background. Meant to click this guy right here. Okay. Let's take a material. First off, let's go back into here. Uh, let's put the speed of light onto our stack. Okay, so let's take this and we're going to divide by square root of dielectric constant. In this case, let's assume a dielectric constant of 4.0, a pretty average number for most of the materials we use in our boards. So square root of 4 is 2. I'll divide that by 2, and I have 491 million feet per second as our speed of light, right? Okay. So I'm going to work in English units here. You could do this in metric if you want it. I'm set up for English, so I'm going to use that one right here. Okay. Now, that's my velocity of propagation, and I'm going to go over here, and I'm going to convert this to inches per second, right? Okay. So, and what I'm going to do is I'm going to go 1 inch, and I'm going to go we got inches per second, and I got this cool little feature right here, and I get 5.901426 blah 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 inches per second. So I get about 6 billion inches per second, right? Okay. Now, here's what I'm going to do. And I'm going to take this and I'm going to say, what if my rise time, now let me just duplicate that because we're going to use it twice here. What if my rise time was 1 nanosecond, right? So 1 nanosecond, and I'm going to multiply that. And I'm going to see that with a 1 nanosecond edge rate, my signal can propagate almost 6 inches on my board with no fear of reflections or crosstalk or those, well, no significant signal integrity issues because the length of my trace is well above the rise time or fall time. Okay. I'm going to do the same thing here, but what if I was 100 picosecond? So 0.1, I went from 6 inches to half an inch right here, approximately, right? So just by changing that rise time to the faster and faster rise time, now this means that my digital signal that used to be able to travel 6 inches on my board with little to no signal integrity issues, reflections, or anything like that, now it can only travel half an inch. 6 inches? Yeah. Most designs I do for, and that most of us will do, very rarely are we going to have traces longer than 6 inches without having some other device, a different device that it connects to and so on that's going to act as a buffer or put a buffer in or whatever. Half an inch, that's quite a bit more challenging. That's a very, very short trace. So you can see here that regardless of clock frequency, you'll notice here none of this had frequency in it. Same material, same dielectric constant, speed of light, same velocity of propagation, just by changing the rise time, just by going to smaller and smaller silicon devices, which is out of our control. As designers, we go to DigiKey, we buy our digital devices, our excuse me, I'm getting over something in my throat from this weekend. Anyways, yeah, we go to DigiKey or wherever we buy our devices, we have no control to say, I want you to still buy the silicon devices that are made from the early 2000s silicon that are, in 180 nanometer process node size. Instead, we're in, 12 nanometer, 16 nanometer, whatever it is. there's a device I use in some of my designs from Xilinx, 250 picosecond edge rates. I got a buddy that works at Qualcomm, 100 picosecond edge rates they're working on, and so on, even sub 100 picosecond. So I want this to be very clear that this is solely a function of silicon design. And just by changing that silicon design, which changes our rise time and fall time, we start having these kind of signal integrity problems and this need to add signal integrity, because even though nothing else in the design has changed, I cannot propagate that signal near as far on my board as I used to and still have it actively driving. The active driving is done in a fraction of a second, so now it's my traces. Now I have to start dealing with those issues. And this is, we basically just did the experiment on this. Using the equation and knowing the rise or fall time of a signal, we can determine how far along the trace the signal will travel while it is being actively driven, i.e. during rise or fall time. If your trace is longer than the propagation distance of the signal edge, you will need to provide for these signal integrity issues. The length of that switching edge is going to be referred to as transition electrical length, or TEL, and the length defined as 1/2 of the TEL is going to be defined as the critical length. Okay? Lines longer than the TEL are likely to fail from reflections because you are no longer actively driving, and lines longer than critical length are uh, and less than the TEL are likely to fail from crosstalk. While technically crosstalk can exist even with signals greater than the TEL, the issue here is that with the once you've passed TEL, unless you have provided for, say, reflection control in the case of series terminations, which we're going to talk to here, um, if we have not provided for proper termination, then the overshoot or undershoot is going to dominate over the amount, typically over what you would get from a crosstalk. So that's why we focus our crosstalk concerns on those lengths that are greater than the critical and less than the TEL. While you can technically have crosstalk on any trace length, but you're typically going to fail more accurately from the reflections if you have not provided for signal integrity. Okay, now the relationship between the E field and the H field in a conductor is shown here. When considering it in 3D, the structure of the PCB will direct the flow of some of the EM energy not only through the conductors, but also through the areas between the conductors, the E field lines between the conductive features. So remember that we said at the beginning that the E field and the H field are perpendicular to each other. The E field, or electric field, is created by our capacitive term, the parasitic capacitance of our transmission line. So whenever I have a conductor here and I have a return plane right here, a mirror plane, to a physicist, this looks like a capacitor. I have a conductor here of some area. I have a conductor here of some area. I have a distance between these conductive plates, and I have a dielectric between them. This, to any physicist or engineer, looks like a capacitive structure, and therefore the E field lines will want to form, as we would in a capacitor, they will form between the conductive plate formed by the conductor and the conductive surface formed by our plane in the dielectric material between them. Once the E field lines are formed, the H field or magnetic field lines must, and again, without getting into black magic RF special cases, um, in general, in the 99.9% of cases, the H field lines must form 90 degrees perpendicular to the E field line. So each time the E field line spreads, the H field line will spread. Okay? So the further the area is, and we'll talk about this here in a moment, the greater the distance between the conductor and the plane right here, the more area between the two conductors, and therefore the more area the E field lines will spread out. The further the E field lines, because the E field lines are going to spread, they're naturally, by the nature of E field, they will spread to fill in the area under the conductor right here, right? So the closer I can get this conductor to this plane, the more concentrated these field lines, so we'll talk about that in a minute. Additionally, the E-field lines do not care directionality. So if I have, say, a ground plane adjacent right here, some of my E-field lines are going to form this way, some are going to form this way right here. And as we show right here, if I have planes very close to the conductor right here, or copper poor, I'm going to have a significant amount of E-field this way. However, if I spread those out, less of the E field is going to want to go sideways and more is going to want to go this way. They're going to want to go the shortest distance they have to go to get to a conductor in the amount of area. So the nice thing here is that because this vertical wall is very thin compared to this wide horizontal face right here, the majority of the E field lines are still going to want to come down here, but we will get some that way. And if I have no side geometry conductors right here of return, then all the E-field lines are going to go down this way. Again, they're going to fill in the area to make a uniform loop area right here. Okay. Now, due to the effects of the difference of the dielectric constant of the environment, typically air above an external trace and the board material below the external trace, uh, external traces are far more difficult to control impedance compared to internal traces. So with an external trace right here, in the dielectric material of the board itself with the plane below, I have a much smaller area that the E-field lines are spreading out into. While above, with no reference material up here, those E-field lines are going to try to spread off out into space, taking the H-field, the magnetic field lines. Now, in the case of an antenna, we want this. We want an antenna to be able to radiate its electromagnetic energy, radio waves, out into space. In the case of our high-speed digital, this is a bad thing. This is what's going to cause a bunch of crosstalk and other uh, emissive surfaces, right? Radiating surfaces, we call them. Okay. Whereas on the internal structure here, because it's both a homogeneous dielectric material and typically homogeneous distance or uniform distance here, I'm going to get uniform distribution of my E field lines, both above and below, and therefore a uniform geometry of my H field surrounding that conductor. So for this reason, we basically say with digital traces, we want to put those on our internal layers as soon as possible. Basically, get out of the pin of the physical device on the surface, put a via, put it to an internal layer, and try to do all of your digital routing on the internal layers and reserve your two external layers for power distribution, analog signals that are running at relatively low frequencies at a single sinusoid rather than these complex square waves that have all these superimposed harmonics of a sinusoid and so on. The area of the E field and the H field associated with the transmission line are directly related to the distance of the signal trace with respect to the mirror or return. Okay? As previously mentioned, digital traces prefer to be on inner layers. This is due to the need to have the uniform geometry of the EM field around the trace for controlled impedance and other SI controls that we'll talk about here. For a wire with a current flowing out of a page towards the observer, we're going to talk right-hand rule and the directionality, right? The H field, the magnetic field, flows in a loop, right? But is that loop going clockwise or counterclockwise when viewed in cross-section? Well, the right-hand rule from engineering basically says if I take the thumb of my right hand and point the thumb in the direction of the current flow, the fingers of my right hand will naturally curve in the direction of the magnetic field flow or of cycling. So for a wire with the current flowing out of the page or out of the screen towards the observer, right, towards the observer, the right-hand rule indicates that the lines of magnetic flux will flow in a counterclockwise direction as shown. The same wire with its return wire next to it. The return current here flows into the page. So the right-hand rule of the blue positive symbol, right hand pointing away from the screen, fingers of right hand naturally twist in counterclockwise, turn my hand around, thumb pointing towards the screen, Now the fingers of my right hand are rotating or twisting in a clockwise direction. From the right hand rule, the direction of the magnetic lines of flux are opposite direction of the positive wire, and therefore the two magnetic fields will effectively or approximately cancel each other out. I have a positive field next to a negative field, and they will meet and they will cancel each other out. Now, if I have two positive fields, they will tend to repel each other and then they will kind of push away from each other. Again, that's getting into a whole bunch of RF and magnetics engineering outside the scope of this class. But in general, we're going to be concerned with this condition right here. And this is our goal with the design of our return planes. Okay, now that loop area I was talking about, the 3D area created by the signal and the return current path formed in a PCB structure. That's the definition of the loop area right here. And the desire is to have the minimum area possible to limit the interaction of the EMI field of the signal trace with any nearby conductive structures on the PCB or surrounding environment. Or surrounding environment here. Now, just as a reminder here, that structure can be in any orientation, right? So my loop area can be a conductor to the side, a conductor below, and so on. I'm basically trying to create this structure right here. I have my conductor on one side, I have my plane below it, and I'm trying to minimize, this is the loop area I'm primarily concerned with here, that we're going to talk about right here, okay? So let's assume I have two layers of my printed circuit board. I have a return plane here, which is on the layer below. The layer directly above that is a signal layer, and I have a signal trace running on there. Now, this slot that I'm talking about in the plane layer, this is simply a removal of copper. We looked at that last week when we were doing our layout, starting to look at how we create our split plane boundary for our uh, plane area definitions. So this is not a routed machine cut slot through the entire board structure, meaning complete removal of board material. This is simply removal of the copper on the plane layer. So if I have a signal trace right here on the blue layer that I drew in black just for legibility reasons, I have the signal here on the blue layer. The return current is flowing on the green layer here, which I drew in the red, again, just for contrast here. So it's got this small loop area in the z-axis. The return current is flowing directly underneath it until that signal crosses the split. Once it gets the split, there's no material here for that return current to flow in. So the return current must go up and around the split there, and then rejoin, and then continue flowing underneath here. So in the area where that trace crosses over this plane, uh, we will have this significant radiating event or large scale EMI emission right here, because I'll have made this huge magnetic field loop area right here that can impact other devices on my board. It can also act as an EMI radiating surface that radiates out into the environment, causing issues. This goes all the way back to week 2 when we were talking about some of the routing options, and I showed that technique if you do have to cross a split boundary to extend the fat trace of the return so that we had the mirror return, and this is why we're trying to mitigate this type of event from happening right here. Okay. This actually, yeah, let's do these last 2 or 3 slides right here, then we'll take our break and we'll come back and we'll talk about stubs and so on. Okay, and yeah, okay. So care must also be taken in the configuration of connector pinouts and plane clearances. So one of the most often overlooked areas when it comes to return paths is in our connectors, especially when you have double or even triple row connectors where I have pins like this. And remember that the purple color, the purple donuts you see right there, that is not the solder mask, that is the clearance in the plane layer. So if I have this signal right here, pin number 12, TDO, that's what we're going to look at. has a signal connected to it, and the return is connected over here. Well, I can't have the return plane copper directly touching this pad, so we have a clearance. We have that predefined as like 20 mils. But if I have the pins too close to each other and I have too large of a clearance there to ease my manufacturability, what I end up with right here is I have this gap where there's no path. So that return current flows underneath the TDO signal until it gets to this point, which has to flow up and around to get to this point right here. Again, I have a large loop. I have a larger radiating surface. This is a bad thing. Okay, maybe you can talk to your fabricator, and in this one localized area, they're willing to allow you to do a reduced plane boundary clearance. This is a somewhat improved because now the return current still flows underneath, but now instead of having to go all the way up and around, it still has to go underneath. But again, I still have a fairly large loop between this point right here and this point right here. The optimum solution, if it is permitted, this is not always allowed, especially if you're using like an interface connector designed by a third party, say a JTAG programming connector or something where the pinout is predefined by the device you need to connect to this. So you're not always able to do this. But in the case where you can, and this goes back to the old ribbon IDC ribbon cable connectors for like computers, remember your old hard drive cables and your tower computers and stuff, where every other wire was a ground or a return signal. And this is why. So that now your signal of interest is coming in here, if we can, repin the thing so you have a return next to it. So now my return path is from here, and literally I have as close to zero loop area as I can, all the way to the return right here. Same thing here, etc. Again, if permissible, this is a significant improvement in loop area if you're allowed. Again, you're not always allowed to do this, so sometimes you have to accept, that you might have something like this, but at a minimum, talk with your fabricator and see if they're willing to let you go and do a more slightly reduced plane clearance so that you can have a contiguous path here rather than having to go loop area up and around. So on. Last slide right here is how that crossing is going to affect us. So we saw the cartoon picture I did a few slides back. Then you might have, here might be a real example. So you might not have a fully isolated, but maybe I just wanted a quiet area. We kind of looked at this on week 2. I said I'd have a better, less cumbersome image of what that might look like. So it might be something like this. I have some digital signals over here. I have my processor device right here. And let's just assume that my A to D inputs of my processor are somewhere up here on the top right here. And in fact, let me do that. Let's just assume that my A to D converter is up here in this corner. Okay. And so I want to have an analog area right here. So I put the split plane boundary right here to say this area of the return plane, which is the black, as we know from Altium. Now the black represents the return area, wants to have its signals come out here and maybe route in here. But before I even get a chance to route those, I have these digital signals right here, which need to go to the standard digital I/O pins down here. But I neglect to remember that I put the split plane right here. So if I let the router just route those digital signals straight across like this and then go down and over, what's going to end up happening is my return currents will start underneath my digital signals right here. They'll get to split, The return currents must now flow down and around before they can meet back up with these. And by making this large area here, I've now made this large magnetic field, or H field, which which uh, in turn induces a noise or a voltage noise onto the signals that are in this quiet area right here. So not only am I creating this large radiating surface right here, but I'm also now coupling that noise into this quiet area here by making this much larger H field area by causing it to loop all the way down to here. So this is one of the problems we're going to have with these kind of split boundaries, and so on. So care must be taken to ensure that digital signals do not enter our sensitive analog areas. This will, if we do this, it'll increase the loop area of the digital signal and induce or couple noise into the analog area. Okay, we'll come back after break and talk about stubs. This is a great place. Let's take like 10, 11 minutes or so, be back at the 15-minute mark. And as always, I will stay online if anybody's got any questions. All right, is everybody back from break? Excellent. And I'll just ask one more time. Anybody have any questions on the stuff I've talked about so far with signal integrity? All right. So stubs. Stubs are the next area of concern when it comes to signal integrity. Stubs are short segments, usually on controlled impedance traces. They're typically used to connect devices to a signal, and they can cause reflections and impedance discontinuities. Hmm. So let's take a look right here. Let's assume for a second that U100 here is driving a digital signal that needs to talk to U101, U102, and U103. Let's also assume I've defined this as a 50 ohm controlled impedance trace right here. Now, I have 50 ohm impedance right here, but when I get to this point right here, I have 50 ohms going this way, and I'm going to go through some input structure here down to return or ground. I then have a second 50 ohm structure going this way through a similar input structure down to ground. I now effectively have 50 ohms here in parallel with 50 ohms here at this point. So immediately in my digital signal here, right here, or in my transmission line, I will see an impedance discontinuity where I will see a change from 50 ohms to 25 ohms at this point. So I'll have a significant reflection or signal integrity issue here. Now, this is the worst case right here where I go completely length right here. This is a little bit better here where I try to route up and only have a small stub here, but I still have that issue here. This is a worst case scenario right here where it looks like we have deleted a component and left a stub connected to nothing. So this is an antenna. This is a huge reflection point right here. We also have to be careful with pull down resistors like this one right here, where we pull down and this is actually a whatever resistance this pull down is plus our transmission line is in parallel to the 50 ohms right here. Now, if this is sufficiently high resistance right here, it's not a huge problem because our impedance for our transmission lines is typically low, like 50 ohms. So let's assume this is like digital, like 1 or 2, kilo ohm kind of thing. I'm not going to see a huge discontinuity right here, but we do have to be careful and calculate what that characteristic impedance change is, and if it's going to be problematic for us. Speaking of transmission lines, what is a transmission line? How is it implemented in a printed wiring board? More on reflections and crosstalks, overshoot, undershoot, rise time, and fall time. And so on right here. In its simplest form, a transmission line is any pair of conductors that is used to guide the energy in the form of an electromagnetic field from one place to another. In a PCB, a transmission line is a trace and 1 or 2 planes. In order to properly manage the behavior of signals on transmission lines, it's necessary to understand what is actually moving on those lines, and electromagnetic fields are the entities that are in motion on transmission lines. Again, this is from Lee Ritchie's Right the First Time. Okay, so what is a transmission line? Well, when energy moves from one point to another, it does so in a transmission line. As we said in its simplest form, a transmission line is a conductor with a mirror or return path. In other words, all traces on our printed wiring boards are transmission lines. All transmission lines have a characteristic resistance, a characteristic capacitance, and a characteristic inductance, R naught, C naught, and L naught. Together, these will produce a characteristic impedance, Z naught. And I just realized I've been meaning to get rid of that. That is 37. Let me delete that. That is somehow a duplicate slide here. Transmission lines are made from a signal trace to carry the EM energy from its source with a mirror, typically a plane, for the EM energy to return to its source. Okay. A simple schematic of a transmission line you will often see used in analysis is this infinitely distributed model right here, where we have uh, L naught, C naught, R naught, and those are going to form Z. And basically, because it's an infinite series, I will measure the same impedance no matter where along the transmission line I am. Okay. Ground here in this case is simply a representation of the ground plane. Now, remember from course 1 the following two properties. These are the reactance or frequency dependent or frequency varying impedance terms of capacitance and inductance. So x of c for capacitance, 1 over 2 pi fc. For those that took engineering, remember that 2 pi f is given the shorthand notation of omega, so we'd see it as 1 over omega c. And for inductance, it's omega L or 2 pi fL. From this, we can see that as frequency increases, x of L will increase, and as frequency approaches 0, x of C will increase. However, in both cases, R will remain constant and will be a relatively low value. For a transmission line then, because R is a relatively low value and can be effectively ignored, we will simply use the simplified form of impedance using only inductance and capacitance at a given frequency. And the Z naught can be approximated with the following equation. Z naught is equal to L naught over C naught. Take the square root. Okay. From this, we can now come up with an equation for the amount of reflected energy. And I just realized I have the same statement in there twice. Let me go back here and kill that one as well, because I don't need the same slide in there twice. This is what, slide 40. There we go. Okay, so from this, we can see that we will get from this, we can come up with an equation for the amount of reflection on a transmission line. The amount of reflection can be calculated with the following formula. Percent of reflection is ZL minus ZO over ZL plus ZO times 100. And that's to give it in percentage. If you want just a multiplier amount, you simply don't do the multiply by 100, and then you get a coefficient, reflection coefficient rho, which we talked about in course 1. Where ZL is the load impedance of the receiver and Z out is the output impedance of the driver. Reflections that add to the initial wave are called overshoot, and reflections that subtract from this initial wave are called undershoot. For signals that are likely to fail from reflection, a termination is needed to mitigate the overshoot and undershoot, and typically a series resistor very close to the signal driver. Now, what does that transmission line look like to us? Or what is this, putting this all together, what does the circuit of our driver to our receiver look like? Well, out of our driver device right here, there is some output impedance, typically a fairly low value on the order of about 20 to 30 ohms, like we have right here. We then have an impedance of our characteristic impedance of our transmission line right here. We'll have a characteristic impedance Z naught, we'll say 50 ohms right here. And then we'll have our receiver here, which will have an input impedance, typically something relatively high. Most digital devices are CMOS now. The gate is insulated from the rest of the device, so it has a fairly high impedance back to a return path. So we'll say maybe 10K ohms right here. You then have both of those have the return path right here, and we have that mirror return. So that forms our loop right there. Now, back to what I said a few slides ago, that what is actually moving in our transmission line is electromagnetic waves. I said earlier in the first half of the hour, or first half of the class, that electrons move. Yes, electrons are the physical entities that are in motion on our transmission line. But this is the one key area that we have to consider going back to our chemistry classes, chemistry and physics classes, the Fermi energy bands, the electron orbits around our atoms, right? Hopefully we all remember that from chemistry. We have our nucleus, and we have our electrons orbiting our nucleus in distinct energy band orbits, right? Or distinct orbit bands, right? S1, S2, P1, P2, and P3, and so on. All those energy band orbits, right? Okay. Now, it takes a certain amount of energy called the Fermi energy band, or the Fermi energy level, to cause an electron to move from the lower orbit to a higher orbit and eventually to become free. That's what the electromagnetic wave is doing. It's supplying the energy to knock an electron free to allow that charge to move. However, the misconception that a lot of engineers, designers, even other scientists have is that the electron that is knocked free from the atom at the beginning of the transmission line, right? So if you visualize a number of atoms here, if I knock an electron free from the atom right here, that is not the same electron that's going to come out the other end here. So while electrons are in motion, what actually moves is in continuous motion from one end to the other end is actually an electromagnetic wave. In fact, all electricity is electromagnetic waves. We do not have actual power or motion without an EM wave. Yes, it is possible to have a charged electric field without a magnetic field in the form of, say, a charged capacitor that has an open switch, so it's not connected, nowhere for that charge to go. A battery energy storage device, those have E field without H field until they are connected, but no work is being done. Same thing a magnetic field. A rare earth permanent magnet can have an H field without an E field, or a charged inductor that is not actually connected at the moment will for a while there have a charged magnetic field without a E field. But no work, no motion is actually occurring. For there to actually be uh, motion or work being done, we must have both E and H field. Additionally, um, one of the other huge misconceptions from the way we teach electrical engineering in university, and I'm guilty of it myself, is we say that voltage pushes and current flows. This is actually a backwards or a misnomer here. Voltage is an indicator of the magnitude of the presence of the electric field portion of an electromagnetic wave. And current that we measure is an indicator of the magnitude of the presence of the magnetic field that's present. What is actually doing that pushing and flowing is an electromagnetic wave. But due to the complexities of Maxwell's equations and true 3D field solvers, we teach the simplified distributed methodology of voltage pushes, current flows as distinct entities. And it works. I mean, don't get me wrong, it is a fine method. It works, but from a understanding what's really going on in our circuit boards, we have to consider these as three-dimensional electromagnetic waveform structures, and therefore start thinking them in terms of Maxwellian equations, 3D field structures here. Now, back to our discussion here. So series termination. Why is series termination the most common type of termination that we're going to use? Well, it's pretty simple. The reason, also one of the reasons why 50 ohms was selected as the de facto standard transmission line. That's because in order to get this low reflection, and because this is an infinite series, this infinite distribution of distributed model of the RL and C, for our Z naught right here, the driver here is actually not going to see the input impedance of the receiver here. Instead, it's going to see only the impedance of the transmission line. And then down here at this end, the receiver is going to only see as its input the transmission line as now the Z load, not the Z out right here, or the Z load. This will be the Z out right here. So we're going to be concerned with this end. Now, because there is no set standard that dictates to the silicon guys, you must make your output impedance here exactly 25 ohms, right? Due to the nature of how silicon is designed and the geometries and the process variation here, we have some variance in our output impedance right here. So the idea is, so one manufacturer might have designed their silicon with their output impedance is 20 ohms, the next might be 33, one might be 19, and whatever. So all we need to do is figure out or determine from the data sheet what our output impedance of the driver is, know our impedance of our transmission line here, and we simply select a series termination here such that the combination of our series termination plus our output here should equal this. Then we get back from electronics 1 what we call the max power transfer, where we want to set the combination of this impedance plus this impedance equal to each other. And that way we can go back up here to this equation right here. So if Z load is 50 ohms, that's our transmission line, and our output, which will be the sum of our actual driver impedance plus the series termination, if this is 50 and this is 50, that's 0, right? 50 minus 50 is 0, divided by 50 plus 50 is 100. 0 over 100 is 0. 0 times 100 is 0. I get 0 reflection, right? So basically, I want the total impedance of series termination resistor plus my output impedance here to equal my transmission line, and I will get as close to 0 reflection as I can. We will never get perfect 0. That's a near impossibility, but that is the goal right here. Now, there are other various termination methods, but series termination is still going to be our most popular, and I'll explain why here in a minute. Again, taken from Lee Ritchie's book right here, series termination has the driver, the resistor in series, the receiver. Then we have parallel termination. Parallel termination, we're using that to try and basically balance out the termination right here and putting a pull down resistor right here. Then we have what we call the Thevenin, which is a pull down and a pull up. We have the AC parallel, which is a pull down resistor with a capacitor right here. And we have what we call diode here. Note that diode termination is not a true termination per se. Diode termination is a voltage clamp that is designed solely to prevent EOS to the device, but does not necessarily mitigate reflections the way a true termination will. And there's also a chart in Lee Ritchie's book here describing the various termination methods, how to calculate the values, and some of the pros and cons. So series termination, only one part is added. The one downside is it does add a little bit of delay. So if you're struggling with timing and you need extremely fast, say like DDR4, DDR5 type of memory, series termination does add a little bit because we are now adding some additional C along with the, or some additional R with the C. We now have an RC time constant with our transmission line. We do have a slight delay added. However, the nice thing with it is very low power requirement, and it's got good DC noise margin right here. The parallel termination, again, only one part added, very small delay added, but very high power. Again, and how to calculate the value. So the RS for the series termination resistor is simply Z naught minus Z out, like we just talked about. The R for the parallel is simply equal to Z naught. You basically make the parallel termination equal to the uh, uh, characteristic impedance. So, but it's very high power consumption. The Thevenin, two parts are added, same small delay added, same high power consumption, and now you have to go through Thevenin circuit equivalent calculations to determine the pull up and pull down resistor values, so you get this no reflection. The AC network, two parts, small delay added, less power consumption than the standard parallel. The RS is fairly easy here. It is simply equal to Z naught again. However, you now need to do simulations to calculate the value of the C needed based off of the type of signals you're receiving. Diode pair, two parts are added, small delay added, low power consumption. Part values not applicable, not a termination, simply clamps the overshoot. Other problem with the Thevenin, very, very high power consumption. Now let's talk about that, why that is. Okay. So if we remember back from our electronics classes right here, that if I have a power source right here, and I have some R, so this is V, this is R, this is going to be I going this way, and then we have a P across the R here, from here to here, right? So P, as we know from course 1, is V times I, right? Now, and V is equal to I times R. So V over R is equal to I. Well, V is the V of the source. R is the resistance value, so I can calculate the I. But here's the question, okay? Now, so that's pretty straightforward, and V is simply the voltage source here. Let's look at it this way, though. And for this, we will do ideal, because we said very low power. We didn't say zero power, but we said very low power. Okay. Now, I'm going to call this point right here VB, and I'm going to call this point here VA, right here. So we have the R here, and I want to calculate the P. Well, P is equal to V times I, right? But here's my question to you. At some point, let's say there was a switch in here, and at some point, in fact, let me do that right here. We'll put VA right there. So at some point, T0, I close the switch and make a connection, right? My capacitor will have 5 time constants, and I'll charge fully up. So after some time, my capacitor here has charged up to 5 volts. Yes, VB has gotten to 5 volts. Would you all agree with that statement? Yes. After some time, if I close that switch, after some amount of time, my capacitor has gotten to 5 volts. Yes?
Yes.
And because my source is 5 volts, VA is also at 5 volts. So VR is really VA minus VB, right? What's the difference in voltage from one side of the resistor to the other? Well, this is 5 minus 5. My voltage is 0. So it doesn't matter what the current flowing through it is because my voltage across the resistor is 0. So with the series termination right here, because of those capacitors in the transmission line, this is only seeing power consumption during the edge, during the rise or fall time. Once that transmission line is at logic 1 or logic 0, once it's at steady state, at that time, there is 0 voltage difference across this resistor and therefore 0 power consumption. Whereas this one here, the parallel termination, if I go back over here now, if I were to have a parallel termination right here, the entire time that point is at 5 volts right here, I have 5 volts across this resistor and I have continuous power draw. So anytime I'm using the pull up or pull down, I have a much more significant power consumption of my termination part than I do with the series part right here. This is one of the reasons why almost all digital engineers I know, although these other methods are available, will almost always gravitate to the series. The only time we consider the parallel is if there's a timing related issue to where the series termination is adding too much delay, and really that's only at the cutting edge data transfer rates where we're in the, the slight delay from this is too much. Okay, so we talked about those. Okay, crosstalk now. Crosstalk is caused when the signal switching on one trace, called the aggressor, produces a strong enough H field to induce a sufficiently large voltage on an adjacent, called victim trace. We also call these a glitch. We'll often say, hey, I just saw a glitch on the signal. That's crosstalk. As with all things voltage related in printed circuit boards, the primary solution is to increase the separation between the trace to the point where the magnitude of the induced voltage on the victim trace, on the victim nets, is below the level to cause a switch in state. And I'll say, uh, the other way you can do it is basically increasing the space reduces the magnitude. Because if we remember from our physics classes, magnetic field strength is proportional to the square of the distance, right? So if I have, say, two conductors and I have a magnetic field between them and I uh, double the space, I don't get half the field, I get 1/4. If I make 4 times the space, I get 1/16 the field strength and so on. So it's a proportional to square of distance. Now, if I can't increase the separation between the trace to the point where the magnitude of the induced voltage on the victim nets is below, I could, using the discussion back here about our planes, all the way back here, if I can't increase the space between the conductors here, if I can't do this, but if I can reduce the gap between this and this, I'm going to radically more concentrate the E field below, which is going to cause that H field to contract in on itself, and therefore the magnitude of the H field that is interacting with the adjacent signal over here will be a lower magnitude. So now that's a more challenging. There's some more limitations to that based off of manufacturing that we talked about last week, but that is another option as an alternate. But again, our primary solution here is going to be increase the space between them. So what is crosstalk? Again, it's caused primarily by inductive component of the aggressive signal. There are methods for doing capacitive coupling, but that's usually not a crosstalk related issue. That's usually more of just a offset related issue or other problems that we'll see there. Some crosstalk is capacitively coupled, but primarily it's going to be inductively coupled due to those magnetic fields. There are two types of crosstalk we are going to be concerned with in our digital signals, what we call backward crosstalk and forward crosstalk. Not to be confused if you've done any RF engineering or antenna design, near field and far field, those are specifically to antennas and RF dealing with uh, uh, frequency domain analyses and S parameters and so on. For time domain digital signals, we're going to simply talk forward and backward crosstalk. Backward crosstalk is seen near the driver end of the trace. Driver meaning the driver of the aggressor end right here. So here's our aggressor, our driven line. Here's my driver end. Here's my receiver end. Backward crosstalk is going to be seen on the victim trace near the driver end. Right. So seen on the victim trace near the driver end of the aggressor trace. It grows rapidly in amplitude to a saturation, and after saturation, additional parallelism will no longer affect the amplitude. So basically, with all of crosstalk, the longer the two traces are in parallel in close proximity, the greater the magnitude. Um, And let me just do something here. And let me go here. And let me just shrink the text size down one so we can read that a little bit easier. Okay, sorry that the text is a little bit small on your screen. I didn't want to add that in. It's due to the proximity of traces and length of the traces running in parallel. So basically, if I have the two traces running perpendicular to each other, I've got very little actual inductive coupling between them. I only have a very little bit. Okay. Again, it grows rapidly in amplitude saturation. So when I see, so here's this rising edge right here. Here's my driven signal. It starts here and it's going to propagate down my aggressor net right here. At the driver end, I'm going to see a very, very quick spike and then return down. And then on the falling edge, again, I'm going to see a very, very quick spike and then return to nothing. Okay. We don't normally care about these because although I might see a spike, it's usually not long enough duration to cause that change of state to be able to propagate all the way down here to cause the change of state on the victim net's receiver pin. On the other hand, forward crosstalk is more insidious. Again, it's seen at the receiver end. It's going to grow slowly in amplitude, but it will be the same shape as the signal on the driver. So again, what we have here is as the signal propagates at this end, the forward crosstalk will be very little, and then it'll keep growing and growing and growing. And now, how does this happen for us? So let's take a look at a signal right here. Okay. So let's say I have two traces running in parallel right here, and I'll do my black ones right here. Okay. So I go over here. On my victim net, over here, I see nothing. And by the time I get here, I see a little bit. I see a little bit more. And by the time I'm down here, depending on how long they run in parallel, this is signal integrity engineers will have to do this analysis to calculate for you. Depending on the magnitude, you'll have to run some 2D field solvers here. But how can we solve this? Well, what if I take this net right here, and about halfway through, I split the nets, and maybe I double their distance for a while. Now, if I use red, again, we're going to have the same net, and I should have drawn the other one here. But over here, but by the time I get back over here, I've gone flat again because I've increased, so I no longer have that amount of coupling to the point where when I get back here, I have to start back over from zero again, right? So by increasing the spacing of the nets from each other, and you'll see that quite a lot. You'll see some bunch of traces running in parallel, and then they all of a sudden their width spread out to twice their width, twice their clearance for a while. I'm sorry, not width, their clearances. They'll see the clearances spread out for a while, and they come back together, and you'll say, why did the designer do that? And it's to mitigate this type of crosstalk related issue here with this parallelism right here. So that's one way that we can deal with that. Okay. All right. Before we get into PDN network, any questions on the crosstalk? Okay. So let's get into power distribution network here. Typical power distribution network showing parasitic elements. Again, I borrowed this out of Lee Ritchie's book just because he did such a good job of this. Remember from course 1 that the real model of a capacitor, for every physical capacitor that you put on your board, we have a free resistor and a free inductor. We also know that every output pin of all of our devices, such as our ICs and voltage regulators, in this case we're using DC-DC converter, also have inductance and resistance, right? So I have power source. In this case, DC-DC converter, could be linear, could be switching regulator, whatever power source you have some output inductance right here. In this case, sense line, so LR, second LR for the sense lines right here. And then for every physical capacitor we put on our board, whether that's a tantalum or some ceramics right here, for every physical capacitor, I get free resistor, free inductor. Then on my IC chip, the device that actually needs this power, I have input capacitance right here on the input pin, and then both my power pin and my return pin also have lead inductance right here, at least L right here. You'll notice the only device that shows no resistance, no inductance is the PCB itself. This is because when we design planes, our planes are so big and wide that their inductance approaches zero, and because of sheet resistance that we talked about previously, the resistance is near zero or very low value. So because of that, and again, remember from PCB1, that for the real capacitor, for every physical C we put on the board, we get free L and free R. Now, from school, again in university, we teach the basic impedance versus frequency response, that capacitors start as high impedance or opens at DC or low frequencies, and as you go up in frequencies, their impedance decreases until they act like a short. We're taught that mantra. Capacitors act as an open at DC and a short at high frequency. But because of this L term right here, we actually have what we call a self-resonant circuit, meaning there's only a very small frequency where this acts as a low impedance, because above that frequency, the L term right here, the inductive term dominates, because remember we also learned in school that inductors act like a short at DC and an open or a high impedance at high frequencies. So we have the capacitive term right here and the inductive term right here. And also because of the R term right here, we never actually approach zero impedance. We always have some R value right here. So because of this right here, what we are going to have now is a behavior of our capacitors for our board. Now, what we do need to do, now I said that the capacitor of our board has near zero inductance. It doesn't have zero. It will have a little bit of erroneous behavior, and we'll need to do a frequency sweep analysis here of frequency versus impedance sweep right here to characterize the overall impedance response across all frequencies. So we'll see right here that at low frequencies right here, our board has a fairly high impedance right here due to the capacitor of the plane. And at some frequency here, it looks like around a couple hundred kilohertz to a megahertz, we start seeing the drop off right here until we get to hundreds of megahertz right here, local minima. Then we have the inductive term, capacitive term, inductive term, and we get these spikes right here. We call these impedance holes, where the function is at its local maxima, and impedance poles, where we're at our local minima right here. Okay? So the goal of the power distribution network, all those physical capacitors that we put on the board, you know, the everyday sheet says you must put a 0.1 microfarad capacitor at the power pin of every device. The actual desire is to select decoupling caps such that each cap has a self-resonant point at one of the impedance holes of the PCB's frequency response. The goal is to achieve a maximally flat impedance response at all frequencies to have a minimal impedance at all frequencies. The value and physical size uh, value uh, The value, dielectric material, and physical size of the cap will determine the self-resonant frequency. So are you using X7R, Y5V, Z5U? You know, what is your dielectric material? The value, is it 1 mic, 0.1 mic, 0.022, you know, whatever value. And then size, the actual physical case size. A 0.1 microfarad X7R capacitor in an 0805 case has a different self-resonant point than the same 0.1 microfarad X7R material in an 0402 case size, and so on. And also note, there is nothing special about 0.1 microfarad caps for use as decoupling. This came from a data sheet from TI from back in the late 70s, early 80s, where between the silicon geometry at the time and the fact that we were using primarily through-hole ceramic disc caps rather than surface mount multi-layer ceramic caps, the engineers at the time determined that that was the appropriate part to use. But ultimately, what we're trying to do is to get this overall maximally flat response across all frequencies. And the reason being is ultimately what we're trying to do is deal with ground bounce or VCC bounce. And it's because, again, as we showed on the previous slide, within every device, within every single digital device, we effectively have, and we're going to simplify it to show a inverter structure right here, where we have these totem pole MOSFETs right here, PMOS and NMOS, but we have the lead inductance right here, those package inductances. So that means every time the output logic switches from 1 to 0 or 0 to 1, we have the inductance from the VCC path through the FET and then over out here through our transmission line, through our load capacitance and back here to return. Okay? Or we have the other way from return, up from return, going this way, back around this way. Okay? But in either case, these lead inductors, if you remember from school, inductors, when you have a voltage on an inductor and you suddenly take that voltage away or open a switch, the inductor immediately does what we call an inductive kick. It immediately switches its polarity, right, reverses the polarity, and has a huge negative energy kick because it's trying to maintain the current flow in the direction it was already going. So if I open it up, and so all of that noise that we typically see on our digital lines isn't actually noise, it's these instantaneous switching events here. So it's caused by the parasitic, right? Ground bounce is a result of the inductive spike during switching events caused by the parasitic inductance in the device leads. The inductive spike is a result of the delay in the power distribution network response to the higher current demand. So every time one of these inductors switches polarity, doing this bouncer's inductive kick, it's basically looking like a momentary short circuit of the VCC to ground lead right here, which basically the PDN network is trying to say, oh, I need a whole lot more current for this device for that momentary instant in time. But voltage regulation systems, switching regulators, DC-DC converters, linear regulators, are very good at maintaining voltage and very, very slow to respond to change in demand. So during that changing event, that switching event, the VCC rail itself cannot respond fast enough, so that instantaneous current is trying to come out of a capacitor. That's the whole point of the cap. Provide that bucket of charge. All right, so the decoupling caps are used as a bucket of charge to provide this momentary higher current demand during the switching events. Due to the lead inductance of the physical caps, however, they can no longer respond fast enough for this instantaneous switching current. Only the planar capacitor of the PCB has low enough inductance, right? It does no good if this has a inductor in the line if the physical capacitor also has inductance in the line, right? So even though I've got this instantaneous switching demand, I need a instantaneous supply of current to counteract that. But if there's also inductance in this one, it too cannot respond fast enough. So that's where we have our problem. Yes, Mattia.
One question: could or does this actually, so the need for let's say it higher current or for discharge, could this let's say it be the cause for the additional aging of the capacitors then?
No. Aging is typically an environmental related effect, such as humidity, temperature, and other things. Typically, capacitors are designed for switching. They're designed to store charge. So I've never heard of any situation where, lots and lots of switching is causing the capacitor to age. That's usually just a time related. Now, when I say higher current demand, what I mean is not that it's exceeding the normal current, but basically this is saying, let's say I normally during a logic 1 I consume 100 milliamps. I take 100 milliamps in, and then during a logic 0, I'm pushing 100 milliamps out. Each time I switch, I need that 100 milliamps. But if the VCC rail cannot supply that 100 milliamps, it's got to come from somewhere. So when I say higher current switching, I just mean even if it's only 100 milliamps, it's 100 milliamps greater than what the current VCC rail is producing. And it takes time for the VCC rail to come up with that extra current.
Right. So maybe I say it wrong. I actually meant maybe not aging, but overstressing the capacitor if it needs to, let's say it on in a very short note, or very often provide that kind of let's say a huge current spike.
I would not worry about the overstressing. Would be only if the total current or the total voltage. And really, capacitors don't really care about current, they care about voltage. So if based off of your design, right, your capacitor's rated for, say, 25 volts, and you're consistently going to 25 volts, now you're stressing it. If you're 25 volt rated and you're switching 5 volts, you're never approaching its maximum rated working voltage, so you're fine, right? So the stress that the capacitor sees is going to be thermal, moisture, environmental, shock, vibe, and voltage, right? This fast switching, nah, you're going to be fine. Now, I'm going to qualify that by saying there's lots of nuances in there. There's also frequency dependence, right? Certain caps say, here's the maximum frequency you can switch at. That's usually more in your old school, your oil-filled, your polypropylenes and aluminum electrolytics and so on. The ceramics typically don't have hardly any problems like that from an aging. Temperature, yes. Vibration and shock, yes. Moisture, yes. Over voltage, yes. There's usually not.
Okay, thanks.
I know we're right at our time. I've got 2 more slides, guys. If you don't mind hanging out like 5 more minutes, we'll do the last 2 slides. If that's okay with everybody. That way we don't have to do like 2 slides on Wednesday morning. Okay, cool. So due to the plane pair capacitance responding to the instantaneous current, physical caps are now only used to refill the plane cap, right? I talked about this a little bit before and said we'd get into it here. Basically, it's like one of those water features where you have like the bamboo, like the smaller tubes and the bigger tubes, right? The small tube is emptying and filling really quickly, the medium tube a little bit slower, the big cap even slower, right? So the little itty bitty tube is like our plane cap. It's filling and draining really quick. It's instantaneous demanding. The bigger the cap, the longer it takes to charge, the longer it takes to discharge, but it's there. It's got lots of volume, right? So our physical caps, because they cannot respond fast enough anymore, and we're relying on our planar cap to do all of our instantaneous switching. When designed correctly, assuming the plane pair cap is designed correctly, physical caps no longer need to be placed directly at the power pins because we have placed a physical cap. It's called our power plane, our plane pair. All the rest of those physical caps we're soldering down to the board, they're just there to refill the plane, so I can put them anywhere on the board I want. Additionally, we said that inductance is one of our key enemies to the instantaneous current demand from our capacitors, even from our physical cap. So we can try to reduce the physical capacitor inductance of the connections from the physical cap to the plane. Traces on the board. Normally, this would be how we'd lay out a cap, like an 0805 or a 1206 here, right? Normally, we would run a little trace out and then put our via, so we have our little bridge of solder mask right here. But that length, even that short length right there, that adds more inductance to my line. This is a bad thing for power distribution. Well, I can try to bring the vias in closer and maybe tent them so they don't steal the solder mask. I can also try to put multiple vias per pad. Again, the more connection paths I have to the plane, the lower the inductance path is from the physical capacitor into the plane. I can put 2 of them on the ends, 2 of them on the sides, same concept right here. I can also manually extend the size of the pad. So even with these, I've got that little narrowing down right here, that's inductance. I can lower that inductance by making a big wide trace. At a minimum to the midpoint, I actually typically take mine and go all the way up around. So I embed my vias directly in my power pads and so on. So I have a low inductance path right here. Again, I cover it with the solder mask, so only the solder pads are exposed, and I don't have a solder thieving here. And again, this is one of the techniques. So the traces on the PCB add inductance to cap, individual vias add inductance to caps, several methods to reduce the inductance I just talked about. Bring the vias closer together, use multiple vias with traces like you see here and here. Use multiple vias with a solid bus bar of copper to create an even lower inductance path. Then my last slide here is just an existence proof case right here. I will show you a design that I did. This is about 20 years ago. This was half nanosecond edge rates. So even though it was 20 years ago, it was still very, very fast circuits. But you'll see right here, I have a processor. I have a internet port right here. I have FPGA CPLD right here. There was a second one right here, external SD-RAM right here. I had a couple of flash memories here, another SRAM right here, etc. right here. And I have a whole bunch of digital bus drivers on this board right here. Now, these little black guys right here, these are quad resistor networks like we're using. These are basically the exact same resistor network we're already using in the design. But what you'll notice right here, there is not a single orangey hand-colored capacitor anywhere near any of these digital devices right here. Instead, here's my two voltage regulators right here. Here's all of my tantalum capacitors stacked right here. And here's all of my ceramic caps stacked right here. I have the same number on the back side of the board, but I literally have one area of my board. I have all the capacitors right there. Now, this is a flood-filled top layer. So you have that very low inductance path. The vias are direct connect, so it's a solid path from capacitors right to the vias, right into the planes right here, and so on. But effectively what you have right here is exactly what I was talking about on the previous slide. And this design worked the first time with zero signal integrity problems. Ignore the dead bug green wire solution right here. That was a different design related issue that wasn't on me. But from the board design point of view, this board worked right first time. Every cap put in a block, end of the board. No problems in my digital section because we properly designed our planar pair capacitances. All right, I know we went over a few minutes here. Any questions on the signal integrity stuff I went over today?
I have a question. So I have
Sure.
a hard time believing that you can always get away with capacitors in a bank in one area of your board to refill the plane capacitance. Like I'm sure it works for digital signals, but what about when you're getting up in like the power, like your power numbers and usage by let's say you're using an SoC, that's a GPU, CPU, which takes in like 60 watts, 70 watts of power.
Right. So
At
power
that
is
point,
right.
yeah.
Power is a different beast. That's where you have to make sure that you're that we've been talking about routing, right? As long as
Okay.
you've got the total power. In this case, yes, you're taking 60 watts of power in, for example, here, but during an instantaneous switching event, any one of your, or hundreds, let's say, let's say it's just 32-bit, 64-bit. So even if all 64 IO switch at the same time, the speeds of those things are so fast that such a momentary instant in time that this physical capacitor, because of its lead inductance, still can't respond. If you want to put it there, you can, but the physics say that because of the modern switching edges, the modern rise times and falls times of your physical devices, that whole switching event is going to have fully completed before this has even moved half of its charge into that line.
I see.
Right? It's all RLC. It's a self-resonant circuit. Because this has the L and the R term that are not significantly present in the plane, these cannot respond fast enough. You have a rise time or fall time switching event happening in the sub 1 nanosecond times, half nanosecond, quarter nanosecond edge rates. Like I said, there's companies doing stuff now in the 5 nanometer, 4 nanometer, 3 nanometer where they're getting 100 picosecond edge rates. This thing, because of that L term, right, cannot respond that fast. So yeah, you can put there. It's still not going to do anything. It's all going to come out of that plane.
So those, just to be clear, the capacitors you're pointing at in the red box are not really your power rail capacitors.
Yeah, they are.
They're your, oh, they are? Okay.
Yeah. Yeah. Basically, still follow the same rule. Go and sit there and say, count up every power pin, make sure you've got at least one cap per power pin. And then the other thing, which I should probably go back here and add some notes to, when I was talking about this, I made the note there's nothing special, but one of the things you do during this analysis right here, you do that frequency sweep to understand at what frequencies right here you have these local maxima, and then you go to the cap manufacturers. They used to have free tools you could download. Now they want you to run them on their own web pages, but they all have the big guys, the AVX, Chemits, and I think Vishay, even so on, have those little wizard things where you can put in the physical cap, right, and say, oh, I want to find a 0805 0.1 microfarad X7R, whatever cap, and then it'll actually generate you the impedance versus frequency response curve, right? And so you need to pick caps. There's nothing special about 0.1 microfarad. Instead, what you want to do is pick caps whose self-resonant frequency is coincident with one of your board's unique impedance holes right here. So the cap value, the cap physical size, and the cap dielectric constant are going to be what drive you. And normally most of the time, the dielectric value or dielectric material is going to be picked on other things too. Temperature stability, et cetera, all those other things we pick capacitance value, dielectric material from. But you're primarily picking physical size and capacitance such that you want to have a self-resonant point to counteract the impedance hole right here, so that you get this minimally flat response. Then yes, your plane, if you have designed this plane pair correctly with the power distribution network here correctly, then yes, your plane will be able to instantaneously respond to that switching demand, and then the caps are just refilling the plane. Because really, even if you put them close to there, all they're doing is refilling the plane. They're just refilling the plane from a closer distance, but a plane is a plane. It doesn't matter where the charge comes from. It's just charge.
So I guess, sorry, one last question. Where, like, there's going to be a sink of that current, and that filling is in reality going to take maybe a very short time, but it still takes some time. So won't there actually be a slight benefit, like maybe if you're operating in a gigahertz range, to place it closer so that when the current is sunk, the plane can be replenished quicker at that point? Or is that a myth?
That's kind of a myth, because the charge, right, your concern is that, well, the charge is going in here and it has to get over to here, but charge is charge. It's everywhere at the same time. I mean,
Gotcha.
yeah, if you're at all concerned, it's not going to hurt. The point I'm making here is that the reality is the charge for the physical caps only are going to refill the plane if you're at all concerned, and if you have the room. Fine, if you want to put them here, put them here. But it's also okay to not put them here. I've got a high density board. Do I have room to put this many caps around this part? I can't tell you how many times I've consulted with someone, a company or whatever, and they're like, oh, I'm really struggling to get all of my parts in this tight area. And I'm like, well, why do you have your caps there? Did you design your plane right? We look at your plane. Okay, your plane is designed fine. Move your caps over the edge. Now I can put all my parts closer together, and I don't have, mass quantities of physical capacitors around this part. That's kind of where I'm going with that.
Gotcha. Thank.
But great question. Anyways, okay. Any other questions out there? Great question, Bob. All right. If there are no other questions, then I will see everybody on Wednesday.
Okay, thanks. Bye.
All right. Bye, everybody. Hopefully, I didn't cause too many people's heads to explode with this paradigm shifting of the signal integrity. And there's a Dennis out there. Mr. Dennis, how you doing?
Oh, you're on the recording.
Yep. Give me 1 second. Let me have Faisal remove. And you're right. And let me do the thing. And you're right. Let me